Section 6.3, Logarithmic Functions. Next, we're going to define a new type of function, and we're going to call these functions logarithmic functions. Very similar to exponential functions, we're going to work with a value b, which is going to be positive but not equal to 1. The logarithm base b of x, which we're going to write as log base b of x, is the exponent to which b must be raised in order to yield x. In other words, when we say log base b of x equals y, that is equivalent to saying b to the y equals x. Because log base b of x represents an exponent, when we try to evaluate log base b of x, we are answering the question, b to what power is x? There are two special bases that stand out for logarithms. Those are base 10 and base e. Because base 10 and base e happen so frequently for logs, we have different notation for them. First, for base 10, instead of writing log base 10 of x, we'll just simply write log x. Logarithms base 10 are also referred to as the common log. So anytime you see log without a subscript next to the g, you're to assume that it's a logarithm base 10. When the base is e, we're going to write ln of x instead of log base e of x. E, if you recall from our discussions of exponential functions, was referred to as the natural base. So we're going to call logarithms base e the natural log. Oftentimes, to help us solve problems that involve logarithms or exponential functions, it helps to sometimes switch between the two forms. Recall from the definition from the last slide that log base b of x equals y is equivalent to b to the y equals x. The log base b of x equals y, we would call the logarithmic form, while the b to the y equals x we'll call the exponential form. In our first example, we're going to write equations in the logarithmic form. So taking a look at 4 to the y equals x, this is already an exponential form. First, in order to write it in logarithmic form, I want to identify the base. The base of the exponential form is the same as the base of the logarithm. Since 4 is the base of 4 to the y, then 4 is the base of my logarithm. You should make your base about the same size as the hook and the g. That way you don't confuse the 4 for an input. Next, what goes inside of the logarithm? What goes inside of the logarithm is what is coming out of the exponential expression. In other words, the output to the exponential function is the input to the logarithmic function. Here in our example, x is the output of the exponential form. Therefore, x is the input for the logarithmic form. And what should log base 4 of x equal? Well, taking a look at our form, the exponent of b to the y is the output of our logarithmic form. So the input of one form will be the output of the other. Since y is the input in the exponential form, y will be the output in the logarithmic form. Next, we'll write b squared equals 5 in the logarithmic form. First, identifying the base. We can see the base of the exponential form is b, so b will also be the base in the logarithmic form. The output of the exponential form is 5, so 5 will be the input in the logarithmic form. 2 is the input in the exponential form, so it will be the output in the logarithmic form. So b squared equals 5 is equivalent to log base b of 5 equals 2. Next, we're going to write e to the p equals q in logarithmic form. Here, our base is e, so we're not going to write log base e. Remember, e is one of the two special bases. Instead, we're going to write natural log. Now, the input into our logarithm is the output of the exponential form. Since q is the output in the exponential form, q is the input in the logarithmic form. And the natural log of q will equal the input in the exponential form, which is p. So e to the p equals q is equivalent to the natural log of q equals p. Next, we'll write 10 to the x equals 1,000. First, identifying our base. In the exponential form, our base is 10. So our base of the logarithm will also be 10. Since our logarithm is base 10, instead of writing log base 10, we'll simply write log. The input in our logarithm will be 1,000, which is the output in the exponential form. And log of 1,000 is going to equal the input in the exponential form, which is x. So 10 to the x equals 1,000 is equivalent to saying log of 1,000 equals x. Next, we're going to write the following equations in exponential form. So we're starting off with log base b of 5 equals 7. Just like when we were writing exponential form to logarithmic form, the first thing we want to do is identify our base. Our base of our logarithm is b. And remember, the base is about the same size as the hook and g. The base in the logarithmic form is the base in the exponential form. What would be the exponent of b? Well, the exponent is the input in the exponential form, which would be the output in the logarithmic form. So 7 would be the exponent. And what would b to the 7 be equal to? Well, the output of b to the 7 is equal to the input of the logarithmic form, which is 5. So our exponential form is b to the 7th equals 5. Next, log of x equals -3. First note, we don't see a base explicitly written next to the little hook of g in our logarithmic form. That means we're dealing with the common log, which means the base is 10. 10 would be raised to what power? The power is the input in the exponential form, so the power would be the output in the logarithmic form. So our exponent would be -3, and what would 10 to the -3 equal to? The output of 10 to the -3 would equal the input of the logarithmic form, which is x. So we have 10 to the -3 equals x. Next, we have log base 3 of z equals a. Our base is 3. Input in our exponential form is the output of our logarithmic form, which is a. And the output of 3 to the a would be the input in our logarithmic form, which is z. So log base 3 of z equals a is equivalent to 3 to the a equals z. Next, natural log of x equals 2.5. The natural log is the log base e. The input in our exponential form is the output of our logarithmic form. So we have e raised to the 2.5 power, and that will equal the input into our logarithmic form, which is x. So natural log of x equals 2.5 is equivalent to e to the 2.5 equals x. Next, we're going to evaluate the following without a calculator. First, we're going to look at log base 2 of 16. When we're trying to evaluate logarithms, we're trying to think of the exponent we would need to raise to the base 2 in order to obtain the input. So in this example, we want to think 2 to what power equals 16? Well, 2 to the first is 2, 2 squared is 4, 2 cubed is 8, 2 to the fourth is 16. So 2 to what power equals 16? That would be 4. So log base 2 of 16 equals 4. Next, we're going to look at log base 4 of 16. 4 to what power equals 16? We know 4 squared equals 16. So 4 to the second power equals 16, which means log base 4 of 16 equals 2. One important thing to highlight in this example is how changing the base does change our answer. It's very important that when we're evaluating logarithms that we do pay attention to the base as well as the input. Next, we'll evaluate log of 1 over 100. Since we don't see a base, we're assuming that the base is 10. So we're trying to figure out 10 to what power equals 1 over 100. Now, this one is a little trickier because we know that if I raise 10 to the first, second, third, or fourth, it gets bigger and bigger. But we do at least know that 10 squared equals 100. But I want 1 over 100. Recall how we evaluate negative exponents. That is, a to the negative n equals 1 over a to the n. So if 10 squared equals 100, then 10 to the negative second would be 1 over 100. So 10 to what power gives us 1 over 100? That'd be negative 2. So log of 1 over 100 equals negative 2. Next, log of 3 equals root 3. So we're trying to evaluate 3 to what power gives us the square root of 3. Whenever we work with nth roots with logarithms, it's very helpful to rewrite them as exponents. Recall that the nth root of a equals a to the 1 over n. So the square root of 3, even though there's not an n written, we assume that the index is 2. So the square root of 3 is the same as 3 to the 1/2. So 3 to what power gives us 3 to the 1/2? The question answers itself. It'll be the 1/2 power. So log base 3 of the square root of 3 equals 1/2. Next, we'll take a look at natural log of e to the 5.2. With the natural log, the base is e. So we're asking ourselves e to what power equals e to the 5.2. Well, just like in the last example, the question answers itself. It'd be 5.2. So the natural log of e to the 5.2 equals 5.2. Next, we're going to evaluate e raised to the natural log of 15.2. This is a little different than the other examples we were evaluating before. We can evaluate it by thinking about what natural log of 15.2 represents. The natural log of 15.2 represents the exponent we would have to raise e to in order to obtain 15.2. So if I'm raising e to this exponent, then by definition, it would equal 15.2. And the next example, 2.3 raised to the log base 2.3, the square root of 2.3, the idea of how to evaluate it is very similar. Log of 2.3 of the square root of 2.3 represents the power we would need to raise 2.3 to in order to obtain the square root of 2.3. So 2.3 raised to the power that we would need to obtain the square root of 2.3 would be equal to the square root of 2.3. In the next example, we have the natural log of the fifth root of e to the fourth power. Natural log is base e. So we're trying to think of e to what power gives us the fifth root of e to the fourth. Very similar to what we did with the square root of 3 a few examples ago. We're going to rewrite our fifth root of e to the fourth, so that way we have a fraction exponent. And now we're trying to ask e to what power is equal to e to the 4/5. Just like in previous examples, the question answers itself, and we would get 4/5. So the natural log of the fifth root of e to the fourth equals 4/5. Next, we're going to evaluate the following using a calculator. First, we're going to look at the natural log of 16. Let's say we could not use a calculator to evaluate. We want to think to ourselves, e to what power is equal to 16? I can't think of anything that comes to mind, especially since e is irrational. It's very hard to evaluate e to various powers, and I can't think of any that would give me 16. So what we can do is go to our calculator. Most old scientific calculators, or even old graphing calculators, can only handle logs of 2 bases. Those are base e, the natural log, or base 10, the common log. In order to find the natural or common log in the Desmos scientific calculator, you want to hit function, and then you can see natural log and common log side by side down here. You can also type it in from your keyboard, typing ln for natural log, and then parentheses for the input. And we can see from the calculator, rounding to 4 decimal places, we get 2.7726. Next, we'll look at log of 1,528. Because this is the common log, no base is written. We're trying to figure out 10 to what power is 1,528. Well, just like in the previous example, no power comes to mind right away. So going into Desmos, we can type in log or hit the log button and then enter our input. And we get 3.1841 after rounding the 4 decimal places. One thing to keep in mind is most scientific calculators can only handle base 10 and base e. Some newer calculators may be able to handle base 2, base 3, base 4, or any base we choose. In a future section, we'll look at properties of logarithms that will allow us to rewrite the logarithm into either a logarithm of base 10 or a logarithm of base e to allow us to use any scientific calculator to evaluate it. Next, we're going to solve the following equations. Our first equation is log base b of 5 equals 7. One thing to keep in mind is log base b itself represents a function. We can't just divide by a function. We can divide by log base b of 5 if we wanted to, but I couldn't physically divide by log base b without it inside. The only way a logarithm makes sense, or a function makes sense in general, is if there's something plugged into it. Looking at this equation immediately, I can't think of a way to isolate b. So we're going to change our perspective of the problem by rewriting it into its equivalent exponential form. The equivalent exponential form is b to the 7th equals 5. Now I see a way to solve for b. Because we're in the form b to the 7th equals 5, we can take the 7th root of both sides. On the left-hand side, the 7th power and the 7th root will cancel, leaving us with b. On the right-hand side, I can't do anything to simplify the 7th root of 5, so I'll keep it as the 7th root of 5. Second, because I took an odd root, then I will not put a plus or minus. One thing to keep in mind, since we were solving for b, our base is always positive and not equal to 1. So make sure you're on the lookout for that. If the situation of plus or minus does arise, you would have to throw out the minus. Or if you get that your base is going to be equal to 1, then that's a sign that you had no solution. Next, we're going to solve log of x equals -3. Well, recall from the previous problem, I can't divide by log on both sides to isolate x. Remember, log is a function, not a variable or a combination of variables. So log only makes sense if there's something inputted into the log. So just like in the previous problem, since there's no obvious way yet for me to isolate x, we're going to rewrite our equation in logarithmic form into its equivalent exponential form. Because we're working with the common log, the base is 10. So log of x equals -3 is equivalent to 10 to the -3rd equals x. In the exponential form, the x is already isolated. All I have to do is evaluate the 10 to the -3rd, and I get 1 over 1,000. So x equals 1 over 1,000. Next, we're going to evaluate the natural log of x plus 5 equals 15. Just like with the log and the log base b before, I cannot divide both sides by natural log. The natural log only makes sense if there's an input, since the natural log is a function, not a variable. Since I don't see an obvious way right now to isolate the x, we're going to rewrite our logarithmic equation into its exponential form. Since we're working with the natural log, the base is e, so natural log of x plus 5 equals 15 is equivalent to e to the 15 equals x plus 5. Now we can see that in order to isolate x, we just need to subtract 5 from both sides. So we get x equals e to the 15 minus 5. Since e is irrational, this answer would also be irrational. So if I want the exact solution, I would keep it as e to the 15 minus 5. If you want to approximate it, you can throw e to the 15 minus 5 in the calculator and round to wherever the instructions tell you. Next, we're going to solve the equation log base 2 of x plus 2 equals log base 2 of x plus log base 2 of 3. Just like before, I can't divide both sides by log base 2. Log base 2 is a function, not a variable. But what we can do, just like in the previous examples, is rewrite it in its equivalent exponential form. When we do, be very careful with all of the additional logs. The right-hand side, we're going to treat as the output of the logarithm. Now, 2 will be our base. The exponent, the input in the exponential form, is the output of the logarithmic form, which here is the log base 2 of x plus the log base 2 of 3. And this will equal the input in the logarithmic form, which is x plus 2. Now, how do we simplify the left-hand side? To simplify the left-hand side, we're going to use our exponent properties. Recall that a to the m times a to the n equals a to the m plus n, meaning if we multiply two numbers together with the same base, we have their exponents. We're going to apply this property to the left-hand side, but in reverse. Since I have 2 raised to the sum of 2 numbers, I can write it as a product where I have 2 raised to the log base 2 of x times 2 to the log base 2 of 3. And now I can evaluate each expression. 2 raised to the log base 2 of x, well, recall log base 2 of x represents the power I would need to raise 2 to in order to obtain x. So 2 to the log base 2 of x will equal x. Log base 2 of 3 represents the power I would have to raise 2 to in order to obtain 3. So 2 raised to the log base 2 of 3 would equal 3. So our left-hand side simplifies to x times 3, or 3x. So after rewriting our equation into logarithmic form, we've obtained a linear equation, which we can solve by subtracting x from both sides and dividing both sides by 2. So our solution to the equation is x equals 1.